So, and welcome to the last lecture of OCSP. Thank you so much for all your work these 7 weeks. And so today we're going to be continuing talking about NMR from what we were talking on Wednesday. And let's just load. Okay, so just a brief overview about NMR spectroscopy using other nuclei besides hydrogen. So as we said before on Wednesday, any nucleus with a nuclear spin can be studied using NMR. And so any nucleus, that means any nucleus with an odd mass or an odd atomic number can be studied using NMR. And so one key concept is that different nuclei absorb energy at very different frequency ranges. And so that's why you don't see signals from other nuclei in certain NMR spectroscopies, even if they are also active, they also have nuclear spin. So that's why when we were looking at proton NMR on Wednesday, we didn't see other signals from other nuclei. Even if we had something like fluorine, which also has a nuclear spin, we didn't see any signals from that because it has very different frequency ranges. And so when we're doing proton NMR, we don't even see signals from deuterium or tritium because even though those are both hydrogens, those are both hydrogen isotopes, and they have very different frequency ranges, and so they're not going. The signal you see from those is not going to affect. It's not going to be shown in proton NMR. And so that's very key to understand when we're looking at other NMR spectroscopies. We're not going to see those proton signals. We're just going to be looking at the nuclei that we're focused on. And we're looking at organic molecules. It makes sense to focus specifically on hydrogen and carbons, right? Because that's what our frameworks are going to be made up of basically all the time. And so with hydrogen, it's very easy. Most abundant isotope of hydrogen does have nuclear spin. If we're looking at carbon, there's a few more complications. And so for the most common isotope of carbon, carbon-12, that's not going to have nuclear spin because it has an even mass number and an even atomic number. So that's not going to have nuclear spin. So if we're going to look at carbon, we have to look at a specific isotope of carbon, carbon-13, which will have nuclear spin because, as we can see, 13, it has an odd mass. On the other hand, this isotope has very low abundance. It only has like a 1.1% natural abundance. And so because of that, there's some complications when we're doing NMR. So if you have a single molecule of your compound, you're not going to be able to figure out the connectivities just based on that, because the chances of every single carbon in that molecule being carbon-13 is astronomically low. It's just essentially never going to happen. So instead, you have a very large amount of your compound, which makes sense because even normally when you're doing any test, very rarely you're just going to put like a single molecule into your machine and run the experiment. Normally you're going to have a large amount anyway. But because of this, because you have a large amount, let's say you have a compound with 5 carbons. Your first carbon, there's going to be some molecules that have carbon-13 in that first carbon. And there's going to be some amount of molecules of carbon-13 in that second carbon, and so on and so forth. And so when you run NMR, you're going to have a bunch of different signals. You're going to have 5 different signals from each different carbon position from some or more of your molecules. And so because of that, you can gather all those signals together. And there's not going to be any competing signals from carbon-12 because it's not going to have nuclear spin. So you just see these carbon-13 signals and you assemble them all together, and you can get the signals from every single carbon. Another trait about carbon NMR is just due to the magnetic properties of carbon, it's naturally going to have a weaker resonance intensity to HNMR. So like, as we said before, we had to use a large amount of the compound anyway. So we also still have to use a large amount just because the signal from each carbon is going to be very, very low. So you're going to need a lot of different carbon-13 spectrum, and then you need to add them together to create a resonance intensity that's the same power as HNMR. For the most part in our class, we're not going to be focused too much on how exactly we're getting these signals, like the technology involved. We're more going to be involved in like the finished plot. So we're going to already have the plot. You don't need to worry about all the complications of getting it, but just for background information, this is a key concept and understanding how we can use carbon-13, even though it's got very low abundance. So what we are concerned about are things that are going to affect the plot. Things are going to affect how we read them and how we understand about these connectivities and the different environments. So there's a lot of similarities to proton NMR because the key concept is very similar. So you're going to have different peaks that are going to indicate your chemically equivalent sets of carbons. So these are going to be your carbons in different environments. So remember, if it's in a different environment, it's going to have a different resonance. And so trends in chemical shift usually follow that approach in NMR, with a few exceptions that we will be getting into later in this lecture. But for the most part, the differences in chemical shift is going to be dependent on the net magnetic field experienced by the carbon nucleus. That's where shielding comes in. Remember, shielding in this situation is very analogous to shielding for Z effective. So Z effective, the effective attractive force that your valence electron feels is going to be blocked by those shielding electrons. It's not going to feel the full effect, and so it's going to feel a weaker attractive force. So in this case, because the external magnetic field is going to be somewhat blocked by your surrounding electrons, your nucleus is not going to feel the full effect of that net magnetic force and of that external magnetic force. So it's going to feel a smaller net magnetic force or a smaller effective magnetic force. And as we said before on Wednesday, the difference in energy between your spin states is going to be proportional to the strength of your magnetic field. That's how you can get different sensitivities by having a much stronger magnetic field, by having like a stronger in your NMR. So if the actual environment of your compound is reducing that magnetic field, you're going to feel a smaller chemical shift, and so that's going to be reflected in your plot. And also similarly, the plots are going to be very similar. It's still going to have chemical shift and absorbance on your y-axis. Are there any questions so far on any concepts from NMR we covered on Wednesday and what we covered in CNMR so far? So like I said before, the plot, the general layout of the plot is going to be very similar. You have your absorbance, chemical shift, and then you have different peaks. But there's a lot of differences, as you can see in this graph that I'm going to go over. Okay. So as we just saw from the plot, there's a lot of differences. Okay. Is anyone having issues with video?
You're cutting out once in a while on my end. Maybe that's just my Wi-Fi. Anyone want to corroborate that?
Yeah, you're also cutting out for me every once in a while.
Oh, okay, I've already switched to my mobile network. Okay, I think there's nothing else I can do. If you guys can't understand anything I say, feel free to chime in. Also, just you don't have to use chat. Just type, like, unmute yourself and chime in too. That'll be faster. But yeah, I think that's the best I can do for now. Sorry about that. Okay, so differences from proton NMR. So one key difference is that there's going to be a lot of information that you see in proton NMR that you just don't see in carbon NMR. So one thing is that if you remember from proton NMR, when you had your different peaks, they were often split up into subpeaks depending on the adjacent hydrogens, right? Your adjacent hydrogens could split the signal from the hydrogen you were actually looking at, and creating those like singlets or those multiplet peaks. So you actually don't see this in carbon NMR for two reasons. First of all, it's because you don't see any splitting between your carbons, because you're looking specifically at carbon 13, right? And so in order to see splitting, those carbons would have to be adjacent to each other. But as we said before, carbon 13 has a very low natural abundance. And so the odds of two carbon 13 atoms being right next to each other in the exact same molecule is very, very low. So you're not going to see that much of a signal. There are cases where you could somehow increase the abundance of carbon 13 in your molecule, but for the most part in this class, you can just assume that your molecules, your compounds, are going to have the natural abundance of carbon 13, and so you won't see any splitting. Another thing is that you actually could be able to see splitting between carbon 13 and hydrogen. Coupling between that is possible, but the signal from that is usually very confusing and very difficult to read, just because it's not just the adjacent hydrogens that can split your carbon signal, it's even hydrogens further away can do that. And so because of that, we also have very wide peaks that overlap. And so because of that, it's difficult to read. It doesn't provide any useful information. And so for the sake of understanding what's going on, usually experienced people will decouple the signal, and so we'll just see singlet peaks. And so because of that, you're not going to get any information about adjacent hydrogens the same way that you do in HNMR from the peaks. You're just going to see single lines. And we saw that before in the plot that I showed you. All of those carbons were just single lines. They weren't actually like sloped peaks. Another difference is that for carbon-13, peak integration is kind of unreliable. So if you remember peak integration, that's going to be the relative height of your peaks, or technically speaking, the relative area under that peak. And in some cases for carbon-13, that peak height will show the relative heights of the carbons, but this can be pretty unreliable. It is not true in all cases, just because that peak height can also be influenced by other factors. So it's very hard to draw simple conclusions just from the height of those peaks. So there are some cases where you can use the relative heights to make a rough estimate of the amount of the ratios of carbons, but I wouldn't rely entirely on that information. If you do that, it's a good idea to at least check your work using other information available. So, as I said before, oh God. So as we saw, there's some information that's missing from HNMR that in CNMR. There's also a greater range of chemical shifts in carbon NMR compared to proton NMR. And so because of that, your carbons are going to be much more sensitive to changes in the environment. So there are often cases where there's very distinct resonances for carbons that are in very similar environments. And so another benefit of that is that peaks don't usually overlap. So because of that, just looking at a table and looking at the resonances, it can be very easy to identify the exact connectivities and the nearby functional groups of your carbons. So for example, from your textbook, you have these carbons and there's no electronegative atoms here. There's no shielding or de-shielding going on essentially, because it's just carbons connected to carbons. It's mostly the same electronegativity. And you can see even that there's still very drastic differences in the resonances. And we'll go over why different resonances later in this lecture, but as you can see, it's going to be very easy to identify these carbons just based on a table and understanding the trends. So even though we are missing that information about the splitting, and it's oftentimes we're missing information about the relative abundances, through this greater range of chemical shifts, actually still able to deduce a lot of things about carbon NMR. Are there any questions so far? Okay, if not. And so because of this difference in information, there's also a different way that you often approach problems. So one obvious thing is that you're going to have a greater focus on a chemical shift over connectivity, just because you're missing that information about like adjacent hydrogens, adjacent carbons. Actually still some information you can gather about adjacent carbons that's not going to be based off of the splitting pattern. It's going to be based off of chemical shift, which we'll talk about later in this lecture. And so because there's different information available about connectivity, often for carbon NMR, you might not always see problems with like, here's this plot, try to draw out the molecule, although you will see problems like this. A lot of time it's also, carbon NMR can be very useful for differentiating very closely related compounds, especially based on their symmetry. And it's because one key concept is that symmetrical compounds will have fewer non-equivalent sets of carbons. And so I'll demonstrate what I mean based on these two examples. So we have these two compounds. They're both benzene rings that have these two OCH groups attached to them. And so in this one, there's only one plane of symmetry, and it's two planes of symmetry. And so one thing to keep in mind, remember this benzene ring, but due to resonance, we say that even though there's like one double bond here and there's not a double bond here, and you think, oh, that's not symmetrical, but because of resonance, this actually is completely symmetrical molecule. Is everyone clear on why benzene is like this? Just remember, another way to draw benzene would be to draw this hexagon and then a circle in the center, because this double bond is kind of evenly distributed across all these bonds. So that's why this molecule is still symmetrical. But anyway, we have this molecule and it has one plane of symmetry right down here. So these OCHs and these OCHs, so on equal sides of this plane of symmetry. And so because of that, we can look at a plane of symmetry, we can look at an equivalent hydrogen, equivalent carbon, sorry about that, based on this plane of symmetry. So we have this carbon here, and we have this carbon here, that's 1 and 2. And so this carbon here is an equal distance from this plane of symmetry as this carbon. So these two are going to be equivalent. And this carbon is the same distance from this plane of symmetry as this carbon. So these two are equivalent. And then this CH3 that's connected to this oxygen is the same distance from this CH3 from the plane of symmetry. So these are equivalent. So we have 1, 2, 3, 4, 5. 5 carbons on each side of this plane of symmetry. So we have 5 carbon-13 peaks on our plot. In any case, you have this very similar molecule. It has the exact same elements, the exact same bonds. It's just that the connectivities are slightly different, and so the symmetry is different. So in this case, we have 2 planes of symmetry, one here horizontal, one here vertical. And so because of that, we actually have fewer equivalent sets. So we have this carbon here that's across the plane of symmetry from this carbon here. So these two are going to be equivalent. And this carbon here is actually going to be symmetrical to both this one, this carbon, and this carbon, because this one is across the plane of symmetry from this carbon. And this carbon is across the plane of symmetry of this carbon. This carbon is across the plane of symmetry of this carbon. This carbon is across the plane of symmetry of this carbon. So all 4 of these carbons are symmetrical. And then this C over here, it's right across this plane of symmetry from this CH3 over here. These are going to be equivalent. So we have 1, 2, 3 peaks. Is everyone clear on the symmetry here? I know this can be very difficult to visualize. But essentially the concept is if you would, there might be a situation where you're given 2 very similar compounds and that the only difference between them is essentially the symmetry. And then you'd be given 2 different NMR plots and then be told to identify which plot belongs to which compound. That is a question that you might encounter. And so because of that, you can use the symmetry of your compound to identify which is which. Are there any questions? Okay, and I just wanted to show an example of a carbon NMR plot. So what I was to exemplify what I was talking about. So as I said before, the range of your shifts is going to be much bigger. And the range for each specific kind of functional group is also going to be much wider. So for here, you would have a carbon just connected to other acyl groups and other hydrogens, and you still have a very large range of possible numbers. And so because of that, in your peak, it's going to be very few cases where your peaks are going to be overlapping. It's going to be usually, for the most part, going to be easy to identify, easy to distinguish. Are there any questions? Okay, if not, I'll leave the floor to Samantha.
Thank you. Let me go ahead and share my screen. All right, this seems to be working. Someone let me know if it is not. Anyway, I just wanted to look at this table one last time. You may remember from, IR spec and that kind of thing, that you'll find a lot of these kind of cheat sheet guides. This is the one from the textbook that you will likely be using in 3570. If you search online, you're going to see a lot of different ones. I put a few at the very end of this lecture, so when we put it up on Canvas, you can look at those if you want. Remember, just like IR spec, that these general ranges, depending on the source, they may vary a little bit. Doesn't really matter to us which one you use, but do be familiar with whatever one your professor uses when you actually teach this course. All right. And so now I'm going to get into some of the factors that affect chemical shift. So remember, like Jennifer said, chemical shift is generally going to be the most important thing we're looking for when we look at a C13 NMR. So we have a plot, for example, let's say 0 is here. I'm just making up some numbers, but this is going to be in parts per million. Anything that is in this upper range, so the higher numbers are often known as downfield. And this is higher chemical shift. Anything on the other end is upfield, lower chemical shift. You guys know this from Wednesday, but just a nice little review, because I do think it is a little contradictory to what you might think, when you look at this plot. And so one of the general factors that's going to affect chemical shift is going to be your type of functional group that you have. So let's say, oops, my bad. Let's say, for example, we had, let's see if this works again. Let's say, for example, we had an alcohol, right? So let me draw out this alcohol. Remember, I say alcohol, but really the bond we care about here is this C to O, because we are really only focusing on our carbons. We don't care about our hydrogens or whatever. So remember that certain functional groups tend to have certain ranges for the resonance. If we wanted to reference this table, for example, from the textbook, you're going to see down here, this is the C to O bond. Generally, it's anywhere from 40 to 80 ppm. You're going to see some variation depending on the source you use. Some others will say 50 to 100, and that's what I'm going to reference later. And so again, other thing you should notice here is that, of course, they're not showing any of the hydrogens, right? One reason is that these are skeletal structures, and then the other reason being that that's not really the bond we care about. So certain functional groups are going to have certain ranges for their ppm. Something else that's important and also related to this last point is going to be the electronegativity of your attached atoms. And so generally, you guys know this, but when we talk about electronegativity, usually thinking about our fluorines or chlorines, that kind of thing. If you wanted to, you could also think about your really electropositive atoms. And so I will discuss this a lot more on the next slides. But essentially, the idea here is that if your carbon is attached to an electronegative atom, this tends to drive the shift upwards. So it goes down field, which means a higher chemical shift, so a higher number. Hopefully that makes sense. One of the major exceptions to this is iodine, and we did not talk about this much when I took the course, but if you are curious, it has to do with the heavy atom effect. Let me write that down. Feel free to search that if you would like. But essentially, it does the opposite of what you would expect electronegative atoms to do. It essentially brings your shift lower, brings it a little bit upfield. And so something else that is going to be a factor that affects your chemical shift and the positioning of your signals is going to be the type of substituted carbon you have. And so, that could be primary, secondary, tertiary, quaternary, I suppose, that kind of thing. When you look at those carbons, you want to think about what carbons are also attached to your original carbon. I know that's a little bit wordy, but I'll get into that. So hopefully that'll make a little bit more sense. But essentially there, you want to think about, for any given carbon you're looking at, you want to think, what kind of carbon is this? Primary, secondary, tertiary, what kind of attachments does it have? And so I'm going to note here that these are very general rules of thumb. Real C13 NMR tends to be a little bit more nuanced, a little bit more complicated, especially when you have multiple factors at play here. And really how depth you need to know this is going to depend on your professor. I know when Jennifer and I took the course, we really did not cover C13 NMR that heavily. I don't know what the syllabus is looking like this year, but other TAs who have also taken Orgo, feel free to chime in with your experiences here. All right, any questions before I move on? Checking the chat. I don't see anything. Awesome. So now I'm going to move into talking about those factors that I discussed earlier. You're going to see I grouped functional group and electronegativity together. Not much to say about functional group. Generally, that's going to be related to electronegativity. Whatever range a functional group falls into is going to be related to that. I just like to say, look at the table for this. That's the easiest thing to do. And if you're curious about how electronegativity is actually going to be impacting your carbon of choice, remember what Jennifer was talking about earlier with shielding. So for any given carbon, they're going to be partially shielded from the magnetic field by their electron cloud. So let me highlight that. So let's say we had a carbon. Carbon's going to have something like 6 electrons, I believe. These guys are going to be zipping around, somewhat protecting carbon from the magnetic field. Remember, not entirely, but it is decreasing the impact a little bit. And so if, for example, your carbon was attached to a really electronegative element, let me just do oxygen, for example, then remember that oxygen is kind of going to hog some of those electrons, right? And so when this happens, the electron density of carbon is going to decrease, meaning that it is less shielded. Essentially, what oxygen is doing is de-shielding your carbon, getting rid of that shield. And so when this happens, the carbon nucleus is going to resonate with a weaker magnetic field. The way I like to think about it is it's essentially easier to get it to resonate. And so this is why it causes that higher chemical shift, meaning a signal downfield. So if, for example, we started at 0 to 20, these are not the correct numbers. This is just for an example. let's say our regular carbon is something like over here. Maybe an addition of an oxygen is going to drive it up there or something. And so last but not least, this effect of electronegativity is going to increase with the greater number of electronegative atoms. I'm actually going to expand this a little bit. So there we go. There are essentially two parts to this. One is that the effect is going to increase when attached atoms are more electronegative. So again, attached atoms are more electronegative. Second part is going to be the effect increases when more of these electronegative atoms are attached. And I know it just sounds like I said the same thing twice, so I'm going to show you what that means. So for the first one, attached atoms are more electronegative. Let's say, for example, we had some methyl group. Let's give it a fluorine. Let's do some other halogens. I'm going to do oxygen, chlorine, maybe bromine, why not? And then of course, not a halogen, but let's just do a methyl. Methyl, methyl. I'm gonna move this one over just so I have a little bit more room. So let's go ahead and think about the electronegativity and how that's going to impact what we have here. So fluorine, its electronegativity, just for your edification, is something like 3.98, I believe. I'm just going to say 4. Oxygen is 3.4-ish. Chlorine, I think it might actually be 3.16. Going to put 3.2. Bromine is right under 3. And carbon is something like 2.55. And so you're going to note here that we're showing a decreasing electronegativity of the attached group, right, to the original methyl. So how this is going to translate is that the methyl attached to the fluorine is going to have the highest chemical shift at about 71.6 ppm. And it's going to go 50.2, 25.6. These are not numbers you have to know. I'm just showing you the trend. And then finally 7.3. Remember, these are all in ppm. So this is essentially showing you that the electronegativity of the attached group is going to impact the chemical shift where the peak appears for this carbon. And then the second part of that is that the effect is going to increase when you have more electronegative atoms attached. So let's say I wanted to put chlorine on our methyl. Let's say now I wanted to do 2 chlorines. And now you guys know where this is going. 3 chlorines, that is not a chlorine. And finally 4 chlorines. So obviously here, electronegativity for each of these given chlorines is going to be the same. It's going to be that 3.2-ish. But the overall chemical shift for this carbon is going to be a little bit different. So the one with only 1 chlorine is going to be the same as above. So 25.6. The one with 2 is going to be about 54. The one with 3 is going to be 77.2. The one with 4 is going to be 96.1. And hopefully this makes a little bit of sense, because imagine, like we talked about earlier, if your carbon is next to a really electronegative atom, that's going to cause some deshielding. It's going to want to tug away those electrons. So if there are a bunch of electronegative atoms, that's going to be a lot more tugging, a lot more deshielding. Any questions on that so far? All right, chat looks good. Let us keep going. So the next factor we talked about is going to be our type of substituted carbons. And so they're essentially, like last time, they're going to be 2 parts of this. One is that more substituted carbons tend to have a higher chemical shift. So the general methodology for how this goes down is that quaternary carbons are going to have a higher shift than tertiary, which is higher than secondary, higher than primary. Let me go ahead and draw that out for you. So imagine we had this carbon in the middle. Looking at the carbon in the middle, there's a bunch of methyl groups around. That's going to be your quaternary. Let me draw your tertiary. And my bad, let me draw your secondary. Let me move these over first. Oops, there they go. I'm going to put secondary and primary in the same one since we were running out of room. So this is going to be our secondary carbon, and it doesn't really matter which methyl we choose, but let's go ahead and take this one on the very bottom to be our primary, and this should be a CH2. 1, 2, 3, 4, perfect. So let's go through these. Look back at the quaternary carbon. If you were to reference a chart, this is going to be something between 30 to 50 ppm. Our tertiary carbon is going to be somewhere between 60, plain 60. Our secondary will be 15 to 55-ish. And our primary, you'll see some disagreement on this. Some sources will say like 0 to 30, others will say 8 to 30. Generally, I very rarely see anything below 8. But yeah, these are the general trends. So like we talked about, more substituted carbons tend to have a higher chemical shift. And then something else we want to think about is that for any given carbon we are looking at, we also want to look at its neighbors and what kind of carbons those are. And so if a carbon is around a bunch of highly substituted carbons, the signal may shift downfield, i.e. the chemical shift may increase in number. So let me go ahead and draw you structure, and then I will explain what that means. So let's say we had this. This is going to be 1, 2, 3, 4, 5 carbons. And so sometimes what we will do in these cases is, first off, let's discuss what kind of carbons we have. This one in the middle looks to be tertiary to me. The ones on the ends look like they're primary. Other side of the tertiary, I'm going to say that's the secondary. And last but not least, this primary. And so immediately we're going to see that we have a tertiary carbon, we have a secondary carbon. Well, we have these 3 primaries, right? And if you take a look at this structure, hopefully you can determine that these 2 seem to be equivalent carbons. So that will appear on the same peak. Let me highlight that. These will be same peak. This tends to translate into a slightly higher peak height when you get to your C13 NMR plot. Not really a perfect association. For example, like decoupling, like we have to do in order to get our plot, is going to mess up the peak heights a little. So that's when Jennifer was talking about integration as not being super duper helpful. That's why. So we notice here that these 2 primary carbons are the same, but what about this one, right? How do we know if these are going to have the same or different chemical shift? And so what we can do is that for any given carbon, let's look at the carbons that it's directly attached to. So this tertiary carbon is attached to a primary, and a secondary. So what we're going to do is, in order to so-called score this, we're going to take the sum of the attachments. So primary, that's 1, another primary, 1, secondary, 2, 2 plus 1 plus 1. We're going to give this a score of 4. Let me write that down below instead. You could do this for the rest of your carbons. So I'm just going to do these 2 primaries attached to that tertiary. They're only attached to a tertiary. Their score is going to be 3. This secondary carbon is attached to a tertiary and a primary, score of 4. And last but not least, that primary is only attached to a secondary, score of 2. Any questions on how I did scoring? Cool, I'm not seeing anything in the chat. Yeah, so you might be wondering, okay, why is this super helpful? Remember here that scoring really not that helpful in instances where we do have different types of carbons. Like it doesn't really do much to distinguish between tertiary and secondary carbons. Oh, I'm seeing something in the chat. Little bit laggy. Yeah, let me know, is it lagging for other people as well? Let me know if you want me to repeat anything. I will go a little bit slower though, and hopefully that will help. Yeah, thank you for those who DM'd me. Anyway, so going back to this, like I said, scoring is not very helpful in instances where the carbon is different. So this tertiary we know is probably going to have a higher chemical shift according to what we talked about above than the secondary. However, it is helpful for these primary carbons. You're going to notice that these two equivalent ones that we found earlier are going to have a score of 3, whereas this one at the very end is going to have a score of 2. And so because of that, essentially it's going to be kind of like a watered down effect from what we discussed earlier. The fact that these primary carbons have a higher score, they're directly attached to more substituted carbons, is going to make it so that they have a slightly higher chemical shift than your primary carbon with a score of 2. I'm seeing the chat. Would you mind re-explaining an example of scoring? Yeah, let me go over scoring one more time. So scoring, remember, it's kind of this arbitrary method that some people will use. I don't know that Professor Ganem ever mentions it. He doesn't go that into CNMR, at least when we took the course. But you'll see some sources, a couple colleges, I think also the organic chemistry tutor on YouTube will use a scoring method. Basically, a score is going to be the sum, let me write this down, sum of the types of adjacent carbons. I know that's kind of a hefty definition, so let me show you what that looks like again. Remember, when we have any given structure, first thing we want to do is determine what kinds of carbons we have. So for any given carbon, is it primary, secondary, tertiary, maybe even quaternary? So if we look in the middle, this carbon is going to have 1, 2, 3 attachments. This is a tertiary carbon. And so we're going to have to do that for every single carbon. Now that we've done that, we will look at any given carbon. So say this tertiary carbon. In order to score it, we'd actually don't care that it's a tertiary carbon. That'll be helpful later. But what we want to do is we want to look at these attachments. So the 3 attachments here, this primary carbon, and this secondary carbon. And we want to take the sum of those numbers. So primary is just going to be 1, secondary is 2, tertiary is 3. You get the gist. It's going to be 1 plus 1 plus 2 gives you a score of 4. Did that help? Let me look at the chat again. Awesome. Yeah, and so like I said earlier, a higher score basically indicates that your carbons are more likely to have a higher chemical shift. Like I said, this tends to be more helpful in instances where maybe you have like a bunch of primaries or a bunch of secondaries and you don't know how to differentiate them. So if, for example, we said these 2 carbons, these primaries with the score of 3, I'm going to label them A. That signal would have a slightly higher chemical shift than this primary carbon with the score of 2. Let me label that B. So A will be a little bit higher than B. And I will show you what that looks like in an example, Sam. Any questions before we get to those? Awesome. So now we're going to be moving on to practice. So generally, like Jennifer's showing you, you're going to have a plot. I just drew this one out so it doesn't look as funky as the other ones, but it's going to range from 0 to some high number, just depending on whatever molecule you have. And what I like to do first is I actually like to look at the signals I have and try to determine approximately what ppm they're at. So this one on the very right, I'm going to say that's like 14-ish. You can say 15, doesn't really matter. Unless they're really close together, you're usually not going to mess up. I'm going to say the middle is maybe 23. One that is leftmost is maybe like 35-ish. And so now that we've done this, we can actually look at our molecule. And so I'm actually, don't draw this in quite yet, but I'm just going to illustrate something. I think in this molecule, it's not too hard to tell that there is a plane of symmetry kind of going this way. And that because of that, that means these 2 carbons in red and these 2 carbons in blue are going to be equivalent. I think in instances where you get kind of crazy looking molecules, and don't draw this, but like, let's say we had this, I think this it's a little bit harder to tell that, these molecules would all be equivalent, just because there isn't a very obvious plane of symmetry. Of course, you can kind of manipulate this by, for example, just drawing it differently. And that's sometimes what I like to do. So I'm going to go ahead and get rid of those two branches. I sometimes just like to draw out my molecule as a straight chain. And that helps me with both symmetry and also just making sure I don't miss any carbons. And so, like we talked about, we're going to have two sets of equivalent carbons. It's going to be these. And so hopefully this makes sense to you. We have two sets of equivalent carbons, so two pairs, and then this lone guy in the middle. Correspondingly, we have three peaks, right? So these higher peaks, although peak integration, like we talked about, is not always a perfect measure, depending on what problems your professor gives you, you could probably look at this and decide, okay, well, these seem to be approximately twice as high as the shorter peak. Maybe these are the pairs, but let's be careful. So let's go through and look and see if this makes sense. So first thing we want to do is take our molecule, decide what kinds of carbons we have. We don't seem to have any really special functional groups. I don't see any, oxygens, that kind of thing. So this middle carbon is going to be secondary. The ones on either side in blue, also going to be secondary. The ones in red, those are just primary. So immediately we're going to see that we have three secondaries. And if, for example, we weren't even looking at this, we weren't looking at peak heights, what could we do to determine which one is going to have a higher chemical shift? One thing we can do is to score it. So remember, take your carbon, look at what's directly attached. So these two secondaries, 2 plus 2 is going to be 4. Give it a score of 4. For these other secondary carbons in blue, the score is going to be 3. So 2 plus 1, 3 and 3. Carbons in red, it's just going to be 2. They're only attached to a secondary carbon. And so now that we know that, let's go ahead and assign peaks. So I'm just going to say this is peak A, this is peak B, and this is peak C. So now that we know that this middle carbon has the highest score, it's also a secondary carbon in comparison to this primaries, this is probably peak A. Remember, more substituted and also higher score means a higher chemical shift. And next up, these carbons in blue, those are probably going to be B, because in addition to, having a higher score, they're also going to be secondary as opposed to these primaries. Leaves the primaries to be C. And now we're done. And if you wanted to, you might be thinking, why didn't you reference the table here? And you can if you would like. Remember that most of your methyl groups in general are going to be between 0 and 50. In some cases, depending on the types of carbons you have, they could be upwards of 50, but not in a ton of cases. And in these instances, you're going to see that these are all below 50 anyway. Any questions on this problem? All right, I'm not seeing anything. Let me keep going. So next up, this structure, we're going to see immediately there are 3 signals, and there are also only 3 carbons. And so this has to be, there can't be any equivalent carbons here, right? Because this looks like to be a 1-to-1 ratio from signals to carbons. Let me go ahead and just label these A, B, and C. Let's go ahead and kind of guesstimate what ppm they're at. I'm going to say C is at maybe 10-ish. B, I'm guessing, is 25. And then A, maybe like 64, 65. Doesn't really matter. And so now I can look at our structure. I'm not going to draw it out for you, but you could if you'd like. So what you want to do is you want to immediately see that there is a functional group here, right? There is this alcohol, this very electronegative atom in the oxygen. And so I'm not going to make you reference the table. If you want to, though, you're going to see that depending on the source, C to O bond is going to be between 50 to 100 ppm. I believe the Orgo textbook says something a little bit different. I think it might be like within that range. I want to say like 40 to 80. Very close though, so it doesn't super matter for our case. And you're going to notice immediately that there is really only one peak between 50 and 100, right? And it's going to be A. So we're going to know that this carbon attached to that alcohol is going to be our A. Next up, we want to differentiate between these carbons, which one's going to be B and which one's going to be C. If we wanted to, we could go ahead and determine what kinds of carbons we have. So we're going to have a primary on the very left, secondary in the middle. You're going to see that the one attached to an alcohol is also a primary. We can also score them. I think the scores are 2, 2, and 2. You're going to see in this instance, scoring really not helpful, right? These are all the same score. And so what we can look at is the difference between the secondary and this primary carbon. So remember, secondary tends to have a higher chemical shift. That is going to be our B, which is slightly higher than our C. This one has to be our C. And so this is a little bit of what I was talking about earlier, where there is some nuance in the different factors you're going to discuss. So you'll see that this carbon attached to this alcohol is really only a primary carbon, right? So you might be thinking, okay, well, why was this a higher chemical shift as opposed to the secondary carbon, which in general has higher chemical shifts than a primary that is unattached to some functional group? And the reason why is going to be because of the electronegativity of the functional group. Essentially, the detail to which you need to know the priority of these factors is just going to depend on your professor. We didn't go super in depth, so I'm not sure that you will either. They will let you know what you need to know, though. Any questions on this one? All right, I'm not seeing anything. Let us go to the last one. So now this structure, this one is a little bit funky looking, so I will draw it out real quick. H2C, double bond, C. It's going to look something like this. And so once again, we can look at our signals, try to determine approximately where they are. I'm going to label it A, B, C, and D. I'm going to say A is just under 200. You can go 190. I'm just going to say right under 200. B looks like maybe like 140. In that case, perhaps C is 130-ish. D, I would say, is just right at 25. And so once again, this would be an instance where you can reference your table. I will just give you the values though. C to O double bond tends to be 150 to 200 ppm. C to C double bond tends to be 100 to 150 parts per million. C to C single bond, just in case you're curious, like we talked about, generally anywhere from 0 to 50, depending on the source. So now that we know these things, we can go ahead and look at our structures. So immediately we're going to see there is really only one peak in the range of 150 to 200. And that's going to be our C to O double bond. So this carbonyl carbon, this has to be our A. Next up, let's look at the others. So the C to C double bond, this is between 100 and 150. And yep, it makes sense that we would have two peaks, two signals between 100 and 150, because obviously two carbons are going to be affected. So B and C are going to be these two. We don't know which yet, so I'm going to go ahead and skip that. You're going to see that our methyl group at the end, that's going to be from 0 to 50. And also we can just use process of elimination to decide that that has to be D. So now that we've got that down, let's go ahead and try to differentiate between our double bonded carbons. So figure out what type of carbon we have. This H2C is going to be a primary. Let me write that a little bit nicer. This CH is going to be a secondary. If you wanted, you can do the carbonyl secondary. And this methyl is just going to be a primary. Let's go ahead and score them. So this H2C only attached to a secondary, score of 2. This CH attached to a secondary and a primary, it's going to be score 3. Same with that carbonyl carbon. Methyl group is just going to be a 2. And so we're going to see that in this case, both the type of carbon and the score kind of follows the factor that we'd expect it to follow, the trend we'd expect it to follow, and that this secondary carbon, you would imagine, has a higher chemical shift than this primary. It also has a higher score. So from this, we can determine that that must be the slightly higher signal. So the C to H is going to be our B, whereas this H2C is going to be our A. Or no, it's not our A. There we go, our C. There we go. Any questions on that one? I know that one's a little bit more tricky. Cool. I'm not seeing any questions. That is actually it for our practice. You'll see this later on Canvas, but I did put up a couple other charts that I personally like. This one's from Oregon State. This one's from Chemistry Steps. And Jennifer, would you like to take the floor now? Give me 1 second.
Sorry, my computer just froze. Okay, give me a second. Okay, so this is the only slide I have, but yeah, essentially just want to conclude the course. Thank you guys so much for working so hard these 7 weeks. And we just wanted to touch on some of the things we learned. So we hope like the one thing you take away from this class is not necessarily like memorizing everything we taught, because there are some concepts that we didn't get time to cover, but essentially what we were trying to focus on is how you would approach problems, because that is a concept that's not very heavily covered in organic chemistry. There's very little hand holding. There's not as many TAs available to help guide you through how to solve problems. So we hope, if nothing else, you learn how to approach problems and how to identify what you don't know, so that you can get, if you do need to get help, you can quickly identify what you need help with, how you could apply that to problems, and then do really well in the exams. So, so class is almost done, so you guys can go soon. But do you guys have any questions, not only about the concepts that we were talking about today, but like anything about the course in general? When Sam and I were taking the course, this was pre-COVID, and I know this semester it's potentially going to be in person the whole entire semester, so it might be somewhat similar. There might be some key differences, but if you guys have any questions about the course, Sam and I will stay behind and answer any questions that you have.
Don't leave quite yet. We actually have a questionnaire. I'm going to slap it in the chat. If you guys wouldn't mind taking a couple minutes to fill it out, that'd be great. For whomever is taking over this course in the future.
And also another announcement. Remember that your last exam is due tomorrow. It's the last thing you have to do for OCSP, and then you're through. One thing, I made this announcement on Canvas. I'm not sure if anyone saw it, but the first 2 parts of the problem have to do with epoxide synthesis. We left that out of the course this semester just because it's not too complicated of a reaction. But I did include 2 links in my Canvas announcement that kind of introduce the concept. And if you want, you guys can attempt the problem. But if you don't want to do it, that's completely optional. I believe that's all the announcements I have. Yeah.
Good job, everybody.
Yeah. Thank you so much. You guys did really well this semester.
Have a good summer.
This summer.
Yeah, good luck in the fall semester.
Oh yeah.
Thank you.